Hi everyone, my name is Tiagi, and when I last left off yesterday, I said that I was going to make a Unit 2 review video today, but I was looking back on my video from yesterday and I realized that it probably isn't the most efficient way to review and study by going through each unit and just going through the whole unit. And I think it's because the video was way too long, first of all, and also I think that I wasn't really in depth to the topics by trying to cover the whole unit in one video. So what I decided is instead, I'm going to be posting these videos where I just go over hard topics, big topics that I can, do more problems with and explain more in detail, which would hopefully help you guys review better than just having a unit video every day. So tomorrow I'll be doing another topic, and today's topic is integration by integration techniques. So let's get started. So these are the techniques for integration that you need to know. So we'll just go through some problems now, and I'll show you how and when to use each technique. So starting off, let's say we have this problem, integral of 1 plus e to the x squared dx. So in this case, we can't do anything with the problem because we have the square root here. We can't do u sub because if we do u sub, we get ex dx, so that doesn't work. So what we can do is we can expand the function. So we can do 1 plus 2 e to the x plus e squared x, and this is all multiplied by dx. Now we can just solve, integrate each term by term. So we get x plus 2 e to the x plus e squared x over 2 plus c, the constant of integration. So that's using expansion. The next problem, let's say we have this problem. We have the integral of x plus 1 over x squared plus 1 dx. So in this case, u sub doesn't work either because x squared plus 1, we set that u, we get du is 2x dx, which doesn't work because we have x plus 1 in the numerator. So what we can do is what I like to call twist and share. So we can break in this fraction into two terms. We can break it into x squared plus 1 dx. Now here we can use u sub, right? And we can break it up into dx x squared plus 1. So all I did here is I just broke up the fraction to make it easier to integrate each part. Now we can do u sub, so we can say that u equals x squared plus 1, du equals 2x dx. Therefore, this equals 1/2 integral of du over u, which becomes 1/2 ln of u is x squared plus 1. And for this one, what we can do, this is just arctan, right? So this is arctan because it's x squared plus 1 squared. So this is just the basic rule for arctan, so we get that this is arctan of x. And so our final answer is plus arctan of x plus c. Next, this is going to be a similar problem. It'll look similar, but it's a different technique. So for this one, let's say we have the question x squared over x squared plus 1 and dx. So in this case, u sub obviously doesn't work, right? Because we got x squared. Well, u sub I think could work, but there might be an easier way. So one of our techniques is to use long division. So if the degree of the numerator is greater or equal to the highest degree in the denominator, so here the highest degree is 2, highest degree is 2, since they're equal, we can use long division to break this up into more terms. So if we use long division, we get x squared divided by x squared plus 1, so we long divide, and we get this. Now think about it, if we have a, let's break this down, let's say we have a number like 7 divided by 2, right? What we do is we do multiply by 3, right? Because that's 6, and we have remainder 1. So how would we write this as an expression? We'd write it as 3 plus 1/2. So what we do here is we can write it now as 1, that's the answer, plus, sorry, I guess minus in this case, because we have a remainder. The remainder is negative, so minus 1 over x squared plus 1. So this expression, by using long division, now becomes this, right? And so we can put the integral sign there, and it's dx. Now we can just integrate each part. So the first part just becomes x. Second part, that's again arctan, so it becomes x minus arctan of x plus c. So in this case, we used long division because the degree of numerator equaled the degree of not the denominator, the highest degree. Next, let's say we have the question, the integral of dx over 1 plus sine of x. So this one's a little trickier, and if we look at it, there's nothing we can really do by using u sub or twist and share, any of that. So what we have to do is we have to multiply by the conjugate. So if we multiply the top by 1 minus sine x over 1 minus sine of x, and we're allowed to do this again because this term, this expression I'm writing, is just 1, because we have a divided by a, which is just 1. So we're allowed to do this, and once we do this, what we get is we get the integral of 1 minus sine x dx over 1 minus sine squared x. So this is actually a trig identity we can use here. So we know that sine squared x plus cosine squared x equals 1. Therefore, cosine squared x equals 1 minus sine squared x, which is what we have here. So the idea here is by multiplying by the conjugate, what we were able to do is we're now able to say this is a trig identity, right? We're able to plug in cosine squared x. So we broke it down using a multiplying by the conjugate and a trig substitution. Now that it's broken like this, we can see that we can use twist and share to break it down even further and solve it. So if we use twist and share, we get 1 over cosine squared x, which is secant squared x dx minus the integral of cosine x squared, sine of x is on the top, and dx is there. So secant squared x just becomes tangent of x. For the left side, we use u sub, u equals cosine of x, du is negative sine of x dx. So we get, this is the integral, positive integral now, so this becomes positive, of du over u squared. Therefore, this becomes just this just becomes minus 1 over u, right? Because we have u squared, u is negative 2. Therefore, this becomes u minus, 1 over minus 1 over u. And so u is cosine of x, we get 1 cosine of x plus c. So again, the idea, multiply conjugate, break it down. Next. This one's also another tricky integral, but it uses a lot of techniques that I have on the board. So this one, 2x, now should I try to smaller? I need space for this one. The integral of 2x over x squared plus 6x plus 13 dx. So here, the first thing we do is we check if we can do u sub. So we try doing u equals x squared plus 6x plus 13, right? Therefore, du becomes 2x plus 6 dx. So it looked promising in the beginning, right? We had a 2x there. But the issue is we don't have a 6. So if only we could have a 6 in the top, then the u sub would work. Well, if we add and subtract a term, if we add a term and subtract the same term, we can have a 6 in the top. So what the idea here is if we do 2x plus 6 minus 6 over x squared plus 6x plus 13 dx, right? We can now use twist and share here. We can do 2x plus 6 over x squared plus 6x plus 13 dx, which you now see works with the u sub. This works here. And we are left with here minus 6, the integral of dx, x squared plus 6x plus 13. So what I did here, I just moved out the 6 to the front because it's constant. And now we use u sub here, so we get integral of du of over u here we get minus 6, the integral of this, which we can use complete the square to make it into an arctan function. So we use complete the square, we see there's a 6, so we want to do x plus, so 6 divided by 2 is 3, so 3 squared. This works, is going to be x squared. 3 times 2 is 6, 6x, and we're left with a 9, so we have to add a 4. 4 is also 2 squared. Now we can just solve it. Our final answer will be ln of x squared plus 6x plus 13 minus 6. Hold up. Sorry, just give me a second. Sorry about that, I just had to take care of something. So here, let's see, so this is just u, right? We just had u, du is just dx. So we get minus 6 divided by 2 is 3 arctan x plus 3 over 2 plus c. So the idea here is what we did is we were able to add and subtract a term, which then allowed us to break it down, which then allowed us to use u sub and break it down. So adding and subtracting a term is a powerful tool you can use to, cancel out. Sometimes you can cancel out the denominator by adding it, or you can do u sub like this. Next, let's try doing this one. Integral of dx x squared minus 5x plus 6. So in this case, we could try doing a complete the square to make it look like an arctan, but that wouldn't work in this case because we get a negative term for the square part. So instead, what we can do is, because we see that the bottom is factorable, right? So we can factor that into dx x minus 2, x minus 3, and now we can try using partial fractions to break it down and decompose it using partial fractions. So we get 1 over x minus 2 over x minus 3 equals the decomposition a x minus 2 plus b x minus 3. Multiply the whole thing by x minus 2 times x minus 3, we get 1 equals ax minus 3a plus bx minus 2b. So we collect the terms, so a plus b, these both are at x terms, so a plus b. The left-hand side has no x terms, so it equals 0. And we collect the constants, negative 3a minus 2b equals left-hand side constant is 1. So negative 3a minus 2b equals 1. Now we multiply by 2, so we get 2a plus 2b equals 0, and we subtract the equations to solve for a. So we get negative a equals negative 1, so therefore a equals 1. And if a equals 1, then that means that b has to equal negative 1 if we plug it in. Wait. Oh no, I did something wrong. So we were supposed to add the equations together. So if we add the equations together, we get negative a equals 1, so a equals negative 1, b equals 1. That's correct, we plug it in. So now what we get is we get the integral of 1 over x minus 3 dx minus the integral of dx x minus 2. So what I did here is I just plugged it in. I plugged in 1 to b, put that there, and I plugged in negative 1 to a, put that there. And now we can see this is just an easy u sub. If we set u equals x minus 3, we get du equals dx, so this is just ln of x minus 3 minus ln x minus 2 plus c. So the idea here is by using partial fractions, we're able to decompose the function into two fractions, and then we can solve it by using integration techniques that we know, or integration formulas we know. That's partial fractions. Now, the last question we're going to go over today is a integration by parts question. So this one will be the question, the integral of x, ex, dx. So in this case, we know to use integration by parts because we have two functions that we multiplied, and there's no way to use u sub or any other technique. So whenever we have two multiplied, we should automatically think to use integration by parts. So in this case, we have to set a u for integration by parts. To set a u, what I like to use is the acronym LI8, which stands for logarithmic, inverse trig, algebraic, trig, and exponential. So when we're looking for a u, we should first look for logs, then inverse trigs, then so on, using this acronym. So in this case, I see that we have an algebraic and we have an exponential. So because algebraic is above exponential in the acronym, we want to set our u to the algebraic. So we said u equal to x, therefore du is dx. So now we want to set dv, and the reason why we set dv next is because if we look at the formula is the integral of u dv equals uv minus the integral of v du. So we need to make sure that this integral is represented by this. So we have the u already, now we just need to set the dv equal to this entire term. So dv is equal to that entire term, ex dx. And now we need to find v. So v we can find just by integrating it in our heads. So if we integrate that, we get v equals ex. Now we just plug this into our formula. So we get uv, so u times v, x ex, minus the integral of v du, so ex dx. Integrate that, we get x ex minus e to the x plus c. And that was the final question. And so through this review, we were able to go through all the integration techniques, and I explained when you use each and why. That's it for today, guys. Thank you guys all for watching, and be sure to subscribe and for tomorrow's video, and leave a comment down below to let me know how I can improve. Once again, thank you guys all for watching, and I'll see you guys all tomorrow. Bye.